So, as an example, let the set V be n-dimensional real space. That is, the set V consists of ordered n-tuples. And let the set F of scalars be the set of real numbers itself. Then the vectors are ordered n-tuples. And the scalars are real numbers, where we need a way to add two vectors, and so the ordered n-tuple x with coordinates x of 1 through x of n added to the ordered n-tuple with coordinates y sub 1 through y sub n is the ordered n-tuple with coordinates x sub 1 plus y sub 1 and so on through x sub n plus y sub n. So here we have a definition of vector addition where the vectors are ordered n-tuples, and a scalar multiple of an n-tuple, the scalar being the number a, and the n-tuple being the ordered n-tuple having coordinates x sub 1 through x sub n, is the ordered n-tuple with coordinates a times x sub 1 and so on through a times x sub n. So here we have a definition of scalar multiplication of a vector, where again the vector is an ordered n-tuple. Now, the n-dimensional real space is a vector space. Since any linear combination of ordered n-tuples is again an ordered n-tuple. So, earlier in the lecture, we made the distinction in that a vector x is a vector whose components have are the components x sub 1 through x sub n. But we can now see that we no longer need to make a distinction, and that the vector with components x sub 1 through x sub n is essentially the same as the ordered n-tuple itself with coordinates x sub 1 through x sub n. Now, for a vector space whose vectors are ordered n-tuples is sometimes called a coordinate space. So the n-dimensional real space is itself a vector space over a set of scalars, those scalars being the real numbers. And this works for any positive integer n. So in particular, the set of real numbers itself is a vector space over itself, since a times b plus c times d is again a real number for any choice of real numbers a, b, c, and d. So here we have a degenerate case where we're looking at the set of vectors and the set of scalars are the same. Right? So new definition. A subset S of vectors in a vector space V is said to span the space if every vector V in the set V is a linear combination of the vectors in the subset S. In which case, we write that the span of S is the vector space V. So we'll look at an example. Let V be the plane, and let the set V be a vector space over the set of real numbers. That is, the scalars are real numbers. And let the set S consist of the vectors 2, 0, 0, 3, and 1, 1. Then for any vector x having components x and y in the plane, we can quickly see that this vector having components x, y is x over 2 times to the vector 2, 0 plus y over 3 times the vector 0, 3 plus 0 times the vector 1, 1. So every vector in the plane is a linear combination of the vectors in the collection S, the subset S of vectors. And so span S is the vector space, which is the plane. All right? Okay, new definition. A set of vectors I are linearly dependent if there exists scalars C sub I, not all 0, such that the linear combination of those scalar multiples of the vectors gives the 0 vector. If no such scalars exist, then the vectors in the set V sub I are linearly independent. All right, so we'll look at an example. Again, let the set S contain the vectors 2, 0, 0, 3, and 1, 1. Then the vectors in S are linearly dependent since negative 1/2 times the vector 2, 0 plus, or we could say minus 1/3 times the vector 0, 3 plus the vector 1, 1 is the 0 vector. So there does exist scalars, namely negative 1/2, negative 1/3, and 1, for which the linear combination of the vectors in the set S gives the 0 vector. Now, however, the vectors in the set S prime, which we'll give to be the vectors 2, 0 and 0, 3, are linearly independent since a scalar multiple, a linear combination, a times 2, the vector 2, 0 plus b times the vector 0, 3, which gives us the ordered pair 2a, 3b, is the 0 vector only if both the scalars a and b are 0. All right? All right, so new definition. A set B of linearly independent vectors that span a vector space is called a basis for the space. So again, we'll look at an example. Let R squared be a vector space over real scalars, and let the set S consist of the vectors 2, 0 and 0, 3. Then, for every ordered pair xy in the plane, this ordered pair is a linear combination of the vectors in the set S. So the span of the set S is the vector space R squared. Further, a linear combination of these vectors is the 0 vector only if both scalars are 0. So this set is linearly independent, and so the set consisting of the vectors 2, 0 and 0, 3 is a basis for R squared. All right? So new definition. Let n-dimensional real space be a vector space over the scalars consisting of real numbers. The standard basis for this space is the set consisting of vectors e sub I for I ranging from 1 to n, where the jth component in the vector e sub I is the Kronecker delta, or is the same as the Kronecker delta with indices I and j. So let's look at an example. So let R cubed be a vector space over the set R of scalars. The standard basis for three-dimensional real space is the set e sub 1, e sub 2, and e sub 3, where e sub 1 is the vector 1, 0, 0, e sub 2 is the vector 0, 1, 0, and e sub 3 is the vector 0, 0, 1. So notice that for every order triple x, y, z in three-dimensional real space, x, y, z is a linear combination of the basis vectors, a very simple linear combination. And further, a linear combination of these vectors gives the zero vector only if every scalar is 0. Right. Now, an important fact to notice is that each vector in the standard basis for n-dimensional real space is a unit vector. The norm of the vector e sub I is the square root of the sum over the index j from 1 to n of the square of the components in the vector e sub I. Now the components in the vector e sub I is identical to the Kronecker delta with indices ij, and so this is the sum, the square root of the sum over the index j from 1 to n of the square of the Kronecker delta with indices ij. The only non-zero term is when the two indices are the same. So this is the square root of delta ii squared. That is the square root of 1 squared, which is 1. So every vector in the standard basis for n-dimensional real space is a unit vector. Further, every pair of vectors in the standard basis are orthogonal So for I not equal to j, the dot product of the vector e sub I with the vector e sub j is the sum of the product of the components. So I'll use index notation. The components, sum of the products of the components in the vector e sub I and the vector e sub j. Again, the components in the vector e sub I are identical to the Kronecker delta with indices ik, and the components in the vector ej are identical to the Kronecker delta with components or indices jk. Now looking at the first term, the only non-zero term there is when I and k are the same, that is delta I times delta ji. Delta I is the number 1, so this is simply delta ji. Now j and I are never equal, and so this is 0. So the dot product for any pair of vectors in the standard basis is 0, and so the any pair of vectors in the standard basis are orthogonal. And so each pair of vectors in the standard basis are orthonormal. And of course we have a term for this.